Hello and welcome to the continuing videos in the linear algebra series. So in this video, we are going to talk about a special thing called diagonalization. So to motivate that, let's ask this little brief introduction question. So if A is just a random 2 by 2 matrix, we know we can multiply by itself. We know we can square it. So the question I have for you, and feel free to pause the video if you need a moment to think about it, although by this point, maybe the answer to this should be something you would know pretty quickly, is A squared equal to the matrix by squaring things? And similarly, can we do that with general powers? So if you've had a chance to pause the video, if you needed to, hopefully you realize pretty quickly that the answer to this is no. The answer to this is no. It doesn't work this nicely. Multiplying matrices doesn't work out like this. We came up with a way of multiplying matrices that served a purpose, but unfortunately that purpose wasn't we can square every single term. If we wanted to define multiplication by just multiplying every single thing term-wise like we do adding, that's fine. We could have done that, but then we would lose every single property we had for matrix multiplication from wherever section we did matrix multiplication. So the answer to this is no, it doesn't work this nicely. That means squaring matrices is not nice. That means taking big powers of matrices is not nice either. But there is one special type of matrix where that changes. What if A was equal to A0, 0D? If you need a reminder of what that kind of matrix is called, feel free to think about it. But what if we had a diagonal matrix? And because it's a diagonal matrix, I'm going to change A and I'm going to call it D. Is this now true? Well, we took A0, 0D and multiplied it by A0, 0D, then we'll notice row 1, column 1, we do get A times A. Row 1, column 2, we get 0 plus 0, 0, and D times D is D. And we'll notice this nice way of multiplying, which doesn't work in general, works for diagonal matrices. And in general, we can only expect it to work for diagonal matrices, for which the identity is an example. Zero matrices are examples. But just in general, any diagonal matrix is very easy to multiply, either by itself with squaring or even other matrices as well. It's very easy to work with a diagonal matrix. Unfortunately, not every matrix is diagonal. However, in light of a previous video that you probably have just seen before you saw this one, while not every matrix is diagonal, can some matrices be thought of being similar to a diagonal matrix? Specifically, can we write D is equal to P inverse AP for some P? So we want to answer this question, and this is called diagonalization. So taking a random matrix A, can we diagonalize it? Can we make A similar to a diagonal matrix? Because if we can kind of ask ourselves, so we just rearrange this PD P inverse. I'll let you think about why these two things are the same if we wanted to solve for A. If we can do that, then A squared is A times A. Note that that's not the same thing as squaring each one individually. Order matters. That would be PD P inverse, PD P inverse, and P inverse times P is just the identity, and we'd get this. And so if A can be diagonalized, and that's a big if, but if A can be diagonalized, then we can square A by finding its diagonal matrix and squaring D multiplied on the outside. Now that might be overkill for squaring, but I'm going to date this video. A to the 2021 would be P times D to the 2021 P inverse. So while you would never do it this way if you just wanted to square something, if you wanted to raise it to the power of 2021, then we can instantly find a diagonal matrix to the power of 2021 and then multiply on the sides. So this isn't about squaring. This is about finding large powers of a matrix, not small powers. Small powers you just multiply out. But large powers, this method, while somewhat involved, saves you a lot of time in the long run. Because no one wants to multiply a matrix out 2021 times. Or I guess I shouldn't say that. If you really want to, have a good few decades to do that. All right, anyway, let's go back to our big if. Can we diagonalize this matrix? And the idea is, well, yes, if we do the following. So here's the idea. Let's suppose that lambda 1, lambda 2, up to lambda n are eigenvalues. With eigenvectors, v1, v2, up to vn. Guess I should say eigenvalues of A. Now, A is an n by n matrix. We're getting these many things. So right there, that might give us a little bit of concern. But for now, let's just roll with it. And I'm going to let D be equal to the diagonal matrix lambda 1, lambda 2, all the way up to lambda n. And we're going to let P be equal to the matrix whose column vectors are those eigenvalues. We're going to take advantage of some multiplication rules that would come from how we multiply matrices and how diagonal matrices just work so nicely when we're trying to work with them as well. So, let's multiply this out. And so I'm going to not actually multiply PDP inverse because this is P, but we have no idea what P inverse looks like. So I'm not going to write it like that. What we are going to write it like is, what is A times P? So we have A times P. And if we remember back from multiplying matrices out, that would say if you multiply on the left by A, and order is important, if we multiply on the left by A, we get AV1, AV2, all the way up to AVN. But that's a consequence of multiplying on the left. That's why we're doing A times P, we're not doing P times A. As for P times D, well, typically we couldn't do this. The reason we couldn't do this is because if it's P times D, then we'd have to take the first row of P. But our V's are the columns. Our V's are the columns. So we can't usually take advantage of that, except to note that D is a diagonal matrix, which is why that's so important. Lambda 1, lambda 2, all the way up to lambda n. Everything else is zeros. So if we took the first row of P and multiplied it by the first column of D, what are we going to be left with? Well, The only thing that's not 0 is the first entry of V1 multiplied by lambda 1. Everything else is going to be 0. If we took the second row of P and multiplied it by the first column, then again, the only thing that's not 0 would be the second entry of V1 multiplied by lambda 1. And so on and so forth. In other words, the first column of P times D would be lambda 1 times V1. And we could make the same argument if you wanted to take the first row of P times the second column of D. Then that would be the second, the only thing non-zero would be the second entry in the row. In other words, the first component of V2 multiplied by lambda 2. And so on and so forth. Now this is very special because we're dealing with the diagonal matrix. This is true regardless. What makes this special is the fact that we have a diagonal matrix that we're multiplying on the right. That's what makes this happen. All right, and I claim that that means that AP and PD are the same. Feel free to pause the video if you need a little bit more time to digest this, or feel free to just take a random matrix and multiply by a diagonal and see that this is what happens in general if that explanation wasn't quite, didn't make a whole lot of sense to you. Just take a random matrix, multiply on the right by a diagonal matrix, and see that you just end up multiplying by the columns by the corresponding diagonal entry. All right, so again, feel free to pause the video and ask yourself, why is AP have to be equal to PD? The answer to that is because we're dealing with eigenvectors. So note here that we've never actually used, this is true regardless of what matrix we have or what diagonal matrix we have. This statement here is true. What makes them equal is since lambda I and VI are our eigenpairs, we get that AVI is equal to lambda IVI. In other words, AP is equal to P times D. So, this is true. All we needed were n eigenvalues, and we know from our eigenvector stuff or eigenvalue stuff that any matrix n is going to have n eigenvalues. They might be complex, they might not necessarily be real, but we do get our characteristic polynomial has degree n, so we do get n solutions, even if some of them aren't real. And, you know, for every eigenvalue, we have infinitely many eigenvectors, so it shouldn't be hard to even pick these eigenvectors as well. And notice here, we don't need all the eigenvectors, we just need eigenvectors corresponding. So there's one more thing we need to worry about. Specifically, can we go from AP equals PD to D is equal to P inverse DP? Well, the answer to that is no. AP, or correspondingly, A is equal to PD P inverse. Can we make that jump? And the answer to that is, in general, no, because we need something to be true. Yes, if and only if, well, this statement here said nothing about the invertibility of P. We just stuck random eigenvectors into that matrix. That doesn't guarantee us that P is going to be an invertible matrix. For example, if we had the same eigenvalue twice, and we took eigenvectors that were just multiples of each other, then it wouldn't be. Then the determinant would be 0, and Therefore, it wouldn't be invertible. So we can do this if and only if P is invertible. And that happens if and only if the eigenvectors are what we call linearly independent. And you may have seen a full-blown video on linear independence. You might have seen just a little brief introduction to linearly independence and stuff like that. And so, regardless, we have a couple rules that we can use for this. And we'll see them in our examples in class. But the idea is that if we have this condition, and that's not necessarily obvious right now, but if we have this condition, not only can we say A is diagonalizable, the diagonal entries of D will be the eigenvalues, and the column vectors of P will be the eigenvectors, assuming we can find enough of them that are linearly independent that correspond to the eigenvalues. Thankfully, there's a rule that can really help us with this. So we'll call this a theorem. That eigenvectors for different eigenvalues are linearly independent. Where we might get into trouble is if we're solving for eigenvalues and we get a repeated root. We get the same eigenvalue more than once. That's where we might get ourselves into trouble. But as long as we're dealing with different eigenvalues, we're good. And we can tell that, if you think back to the eigenvectors and examples you might have seen in eigenvectors, is that if you had an eigenvector of multiplicity 2, do you get two different, and by different I mean linearly independent eigenvalues when you solve for the eigenspace? If you can get two different ones, or two linearly independent ones, then we're still good here. But if you don't, if you had what we call algebraic multiplicity of 2 on your eigenvalue, it showed up twice when you factored, but you only get one linearly independent eigenvector because you only get one parameter in your eigenspace, then we have a problem and we have something that can't be diagonalized. So we'll wrap it up here. A is diagonalizable if and only if every eigenvalue of algebraic multiplicity K has K linearly independent eigenvectors. And we actually call that the geometric multiplicity. So as long as they match up, so if you are finding your eigenvalues and you get a eigenvalue of 3, but it happened 3 different times, like you factored, you got lambda minus 3 different times, then we need to have 3 parameters in our eigenspace. If we do that, we can get 3 linearly independent eigenvectors and we're good. But if we don't get 3, then unfortunately our matrix would not be diagonalizable. And we would see that in examples in class. And a nice fun little corollary to this is if A has n distinct eigenvalues, so no repeated roots, then it is diagonalizable. That's not an if and only if. You can still be diagonalizable if you get the correct number of eigenvectors for repeated roots. But if you don't have repeated roots, we know we're diagonalizable automatically. So the vast majority of matrices are diagonalizable. Unfortunately, not all of them. This goes a little bit beyond this course, but if it's not diagonalizable, then you can still do something nice. It's called, I forget the exact name off the top of my head, but the idea is you can get matrices that are close to being diagonal, even if they're not exactly diagonalizable, that you can do not quite as nice as taking powers of diagonal matrices, but kind of the next best thing. So fear not, even if it's not diagonalizable in the grand scheme of things, it's not as nice, but nicer things can be done than just squaring and cubing and the power of 2021 of A. All right, so in class, we'll obviously see some examples of this, or well, I guess if I'm your student, you'll see some examples of this. I'm assuming everybody. But the idea here is if we want to diagonalize a matrix, we find the eigenvalues, we find the eigenvectors, we find P. If they are linearly independent, because it's diagonalizable, if we have enough of them, then we can find P inverse and we can diagonalize whatever we'd like. And some nice little applications of that. All right, anyway, that's it for this video. And maybe you'll see you in the next one, if this isn't the last one.